Hello, my name is Sterling, and today we're going to be looking at a potential flow against a flat plate fluid dynamics question. So this question states that potential flow against a flat plate can be described with the stream function psi equals a times xy, where a is constant. This type of flow is commonly called a stagnation point flow since it can be used to describe flow in the vicinity of the stagnation point at O, which is here. By adding a source of strength M at O, stagnation point flow against a flat plate with the bump, as depicted in this figure, is obtained by this figure. Determine the relationship between the bump height h and the constant A and the source strength M. So the first thing we want to do is get our total stream function, which is psi for uniform flow plus psi for source flow. So in this case, AXY is our uniform flow, and for source, that is Q over 2 pi theta, where Q is flow rate, and in our case, that becomes M over 2 pi times theta. So if we plug in, or first we need to convert AXY from Cartesian to polar coordinates, and you do that by setting x equals r cosine theta, y equals r sine theta. So our uniform flow becomes a over 2 times r squared sine of 2 theta. And that was just substituting r cosine x in for, or r cosine theta in for x and r sine theta in for y, and then multiply them out, and due to trig identities they become r squared times sine 2 theta over 2, and then times the constant A. So now getting our total stream function is going to be a over 2 times r squared sine 2 theta plus our source, all right, so our stagnation point happens at point over here. So our stagnation point happens at in xy, it's at 0 comma h, because h being the height of our bump, and in cylindrical coordinates, cylindrical polar coordinates, theta comma r, that is in pi over 2 comma h. So now we want to take a look at our radial and tangential velocity components. For radial velocity, that can be described as 1 over 2 times d psi over d theta. And so that's 1 over r times our derivative of this equation, which becomes ar cosine of 2 theta plus m over 2 pi times r. Now for tangential component, v theta, that can be depicted as negative d psi over dr. So up here we're taking the derivative of our stream function in respect to theta and multiplying it by 1 over r. And now for tangential, we're taking the negative derivative of our stream function in respect to r, which yields ar sine of 2 theta. So now at our point pi over 2 comma h, then we'll have a stagnation point when VR is equal to 0, because V theta is already equal to 0 because if you plug in pi over 2 in for theta, then sine of pi becomes 0. So that's how we know that v sub theta is equivalent to 0. Now we want to solve for VR, setting that equal to 0 is 0 equals, over here we have AR cosine of 2 theta plus m over 2 pi r. Now we're substituting in pi over 2 for our theta and h for our r's. So this becomes 0 equals AH times cosine 2 times pi over 2 is just pi, plus m over 2 pi times h. Cosine of pi becomes -1, so if we rearrange, we have AH equals m over 2 pi times h. And solving for h, we have h on this side, and then m over 2 pi a, square root of that, since your h's are squared. So that is our final answer. And there's my signature. And here's my face. Thank you.